actually changes shape. Remember, it's different from a camera, because with a camera, when you're looking at things far away, you just change the image distance, right? You change the distance. You change the distance between the lens and and wherever the image is being formed in the film or the CCD, the chip, like the image reading chip. And so that's how a camera works, by changing that distance. That's why when you zoom in, your camera goes, or it comes back, or it goes back. It changes the image distance. But the eye, you can't change the image distance. Because the image distance for your eye is always going to be the distance from the lens to the retina. So the image distance for your eye is always going to be this distance. And so when I want to change where the object that I'm looking at, whether it be near or far, I can't change the image distance. I have to change the focal length. So if I have an object that's really far away, if an object is really far away, that means that the light rays are parallel. Remember we talked about how the sun, when we talked about that ray model of light, the sun, the light rays, as they come into you, really they're sort of going out, but by the time they reach you, they're going parallel, at least as far as you're concerned, because you're just seeing such a small little piece of the light from the sun. So those light rays from an object that's really far away object, are going to be parallel to one another by the time they reach your eye, and parallel light rays will focus at the focal point. And that's how we define the focal point for a convex lens. For a concave lens too, but for a convex lens, which is what your eye uses, it has a system of things actually. It has something we call the lens, but then it has other parts too that refract the light. Anyway, this convex lens will focus the light at the focal point. And in lenses, the image is formed where light rays cross. And so when I have the light rays that cross at the focal point, then my image is also formed here. So when I have an object here, my image formed right here. And so my focal length is this distance. When I'm looking at an object far away, the focal length is the length of the eyeball. Okay? This is my focal length. So DI is equal to F. Now let's think about that for just a second. If I have my image distance equal to my focal length, let's write our lens equation. 1 over DI plus 1 over DO is equal to 1 over F. Let's replace DI with F and solve for DO. And then we'll find something that we already know. If I do this, I get 1 over DO equals 1 over F minus 1 over F. What I did here is I said that when my object is really far away, the image distance is equal to the focal length. So I have these parallel rays that come along, they go into the convex lens and they focus at this point, and where the light rays focus, that is my focal length. So if DI is equal to F, then I can rewrite this. I just replace DI with F. And I get 1 over DO equals 1 over F minus 1 over F. And 1 over F minus 1 over F, of course, this is equal to what? Not 1, 0, right. And so I get 1 over DO is equal to 0. Well, how do I get 1 over DO equal to 0? What does that tell me about DO? That it's a small or a big number? No. If I have 1 over a number, and that's equal to 0, what must that number be? Is it going to be a small number or a big number? Now, if I have 1 over a small number, like 1 over, I don't know, 0.1, for example, what's that equal to? 1 over a tenth. That's equal to 10, right? Or no, let's think about it in terms of fractions. Maybe that's easier. If I have 1 over a half, and 1 over a third, which of those is smaller numbers? 1 over 3, rather. Yeah, if I have 1 over 2 or 1 over 3, the 1 over the 3 is the smaller number, right? So the bigger my denominator gets, the bigger the lower part of the fraction gets, then the smaller and smaller the result is. So in order for 1 over DO to be equal to 0, that means DO has to be really big or really small? Really, really big. In fact, we would say that DO is equal to, or really DO approaches infinity. And so the focal length when an object is very far away, the focal length is equal to the image distance. When an object is close, it's a little more complicated. So if I look at something really far away, and then I try to look at something close, your eye has to change. Let me take a little aside, and we'll do a little ray tracing. We're not going to do a whole lot of ray tracing, but it's kind of important just to illustrate this. So if I have a lens, I can draw rays. This lens has 2 focal points. There's a focal point here and a focal point here. I can draw rays in a couple of different ways. Thank you, Stephen. If I have a light ray that is parallel to the axis, it goes through the focal point. If I have a light ray that instead goes through the focal point, it goes parallel to the axis. So if I have 2 light rays on one side of the axis that are not parallel, then the image is going to be a little bit different. And the way that I draw the rays to figure out where the image is, which is where the 2 rays cross, is I let the rays go parallel and then through the focal point. And then I can also draw a ray that's through the focal point and then parallel to the axis. All right? So if I have an image that is closer, let's redraw this eye. On the left, it's an image that's really far away. If I have an image that's closer, say like right there, or an object that's closer, that's my object. I'm going to draw my lens. I'm going to go ahead and draw it the way that I know that it is, which is going to be kind of big and big in the middle like that. The focal points are going to have to be like this, such that if I draw the rays parallel to the axis, through the focal point, and parallel to the axis. So notice what happened here. I still have my image at the retina, at the back of the eyeball. The image always has to be at the back of the eyeball. But what's happened is I've had to draw in my focal length a little bit. Over here, my focal length was at the retina, because I was focusing light rays that were parallel from an object a really, really far distance away, which in terms of the eyeball, it means that the image is a lot farther than the focal length of the eyeball, which is, a couple of centimeters. So the back of the room, for example, would be an object that's an infinite distance away in terms of the eyeball, because it's much, much, much farther than the focal length of the eyeball. So here I get a long skinny lens with a longer focal length. But here, when I'm focusing on something that's closer to me, I have to get a fat lens, sort of a lens that's really thick in the middle, because my focal length is now a lot shorter. We talked about how these lenses, how they look different when they have different focal lengths. Long focal length, short focal length. Don't worry too much about the ray tracing. That's just sort of to get us to where we're going. But I do want you to know that when I look at something that's close, my lens has to get a shorter focal length. And that means physically that there are these muscles in your eye. Those muscles have to squeeze down onto your lens and make it thicker in the middle. It's like you just sort of squish it down so that it gets a shorter focal length. That's what happens when you go from looking at something far away to something close up, that your eye actually changes the shape of the lens. Kind of cool. We don't really have stuff that does that. It's difficult to change the shape of a lens, especially we make lenses out of glass and plastic, and you can't really change the shape of those things. But the human eye is pretty remarkable. It changes the shape of the lens that allows you to look at things that are super far away up to really close, just within 20 centimeters or so of your face. That's why, we'll talk about this a little later, that as you get older, that lens, once you hit 40, sort of go over 40, that lens becomes more rigid, not as flexible as it once was. Those ciliary muscles that change the shape of the lens, they get a little weaker, and it's just harder to look at things up close. That's why when you develop presbyopia, that's what it's called, it's like presby means elder, opia means vision, like older vision. It means that you can't focus on things as close anymore. That's why old people always have the newspaper out like this. You know what I'm talking about? Because they can't look at things that are up close.
Didn't you have an eye doctor appointment?
Today at 10:15. Yeah, we're going to see what they say. All right, so we'll talk more about that in the lens, and we're sort of mixing things up right now, but we'll talk more about glasses and how they affect the eye. The eye is a sphere, pretty much. Ideally, it's a sphere. We'll see that some people have longer eyeballs and some people have shorter eyeballs, and that's why they're either nearsighted or farsighted. The sphere is filled with a fluid, or with a clear fluids. These are called the vitreous and aqueous humor. Remember we talked about that? It contains the lens and the ciliary body, which changes the shape of the lens. You have 3 layers to the wall of the eye. I'll come back and I'll show you that figure that I showed you before, and we'll identify all those different parts of the eye that you'll need to know. But first, let's just talk about the 3 layers to the eye. You have the fibrous layer. This is the outside layer. It consists of the sclera. That's the white part, the whites of their eyes, and the cornea. And that's the clear part. I'm going to grab my model of the eye. Forget to bring it. I'll write that down.
And he said that what it like for it to be
So, you can pop out your eyeball. I dated this girl in high school, and her mother had a glass eye. You know what this? She would take it out, and she would take it out, like while I was there. Like, embarrass your daughter, right? Pop out your eye, or what? Anyway, it didn't look like this. It was just glass here. But the white part is called the sclera, and then the cornea is just the clear part. You need to be careful when you're identifying the eye, because the lens is not the cornea. Now, the cornea is an important part of the refractory device of the eye, the part that refracts light. In fact, most of the refraction happens at the cornea. What's that? Okay. Most of the refraction happens at the cornea. Your book talks about that. And then the lens is really for fine adjusting. Even though we call the lens something different in cameras, the lens is what's this part of the eye, right here. And that's the part that's connected to the ciliary body. Those are those little strands on either side of it that will squish down or stretch out. It's like a fine adjustment of the focal length. But much of the focal length is governed by the cornea, and that doesn't change shape. That's always the same. The what? No, the rods and cones are in the retina, not in the cornea. Yeah, we'll talk about that. They're in the sensory layer.
So is it like always being I don't want to say regenerated, but you know how you can get like a scratch on your eye and then in a few hours.
Yeah,
like,
it can. Yeah, there is. Yeah, so sure, there can be healing within the eye. That's why you have that fluid that comes in. It brings in nutrients to the eye. The vascular is the uvea. It's called. This consists of the choroid, the ciliary body, and the iris. That's a Y at the end. And the iris. The choroid contains the blood vessels. And the ciliary body contains muscles. I think this was a question on your quiz. To change the shape of the lens.
So this is the same as the one up there because you've got the S up there. In the,
Where?
Next to the eyeball. It says the lens and the ciliary body.
Oh no, that's something different. That's the sclera. The sclera is the white part. That's not the ciliary body. The ciliary.
This one.
No, there's no S. No S. There's no S here either. Right? Ciliary. Oh, what one? Oh yes, no S there. Yes, no
Okay.
S. Just C.
Yeah,
Right there. Do I have an S in my notes? No, I just made it up. All right. Sounds like there should be an S. This is the ciliary body right here. It's not labeled on that figure. But again, the lens, which is this fluid-filled pouch, oblong thing, has these muscles attached to it, and they can squeeze down or stretch out. Okay. All right. It contains muscles to change the shape of the lens. And then the iris is an aperture that changes the size of the pupil. The iris is the colored part. The pupil is the hole. So the iris is the portion surrounding the pupil, and then the pupil is like the black dot, which is not really black. It's just, it's a hole there. Yeah. Yeah. The iris prevents spherical aberration. I'm going to tell you. In optical devices, we have different types of aberrations. That means that fuzzy images, the images aren't made just right. And if I have a lens, a convex lens, if I have light rays that come into the outer part of the lens, just because of the spherical shape of the lens, they will focus at a certain point. But if I have light rays that come into the inner part of the lens, they will focus at a slightly different point. So with spherical lenses, it turns out that the focal point is slightly different depending upon which part of the lens you go in. And with cameras, we get rid of this just by blocking the outer parts of the lens. And with the eye, we do the same thing. So what we do, what the iris does, is it just blocks out, but this is a blue-eyed person, it blocks out those outer rays, and that way I don't get this separate focal point. Now when you have two different focal points like that, what that means, you get a fuzzy image. That you get part of the image that's made right here, and then another part of the image that's made right here, and the two just don't match up. The iris, of course, also does something else. What does it do? When the pupil gets smaller, why does your pupil get smaller? What causes the pupil to get Right, yeah. When you have really bright lights, the pupil will get smaller and just limit the amount of light. So we can write that too as a function of the pupil. So it prevents spherical aberration and decreases in size due to brightness.
So, like when you're on drugs and stuff, and they say that your pupils get huge, why? Like, why would that?
No idea. I mean, I think it's a physical thing. It doesn't have to do with the amount of light that you have. Never done drugs. So. All right.
Well, I haven't either,
See, Tristan. The sensory layer. So 3 layers, the fibrous, the vascular, and now the sensory. This is the innermost layer. This is sort of where the detection occurs. It contains the retina. And the retina, if we're looking at the back of our eyeball, the retina is like right here. Remember, it's like the film of your eye. It detects the light that strikes the back of your eyeball and turns that into an electrical signal and sends it to your brain. So the retina converts the light to an electrical signal. The retina contains rods and cones. Rods are for low light conditions. And cones are for bright light. One of these is for colored light, and then one is for just black and white. Which is it? Rods are for what? Black and white or color? You can think about it. When you go outside at night, like in the dusk, what do you see? Do you see bright green colors on the trees and grass, or do you just sort of see gray all around? You see gray, right? Not because the trees are now gray. The trees are still green, and that color is still there. But it's because you're in low light conditions, and in low light conditions, the rods are activated, and they're more active. But rods aren't really sensitive, not very well to color light. So when you go outside at night, you don't see colors very well, not because the colors aren't there, but you don't see colors very well because your eyes are using these rods instead of using the cones.
And there's actually no colors in rods.
Yeah. Babies too. That's why they respond to sort of very stark images of black and white. But I guess they like the multicolored things, but it's more that they like great contrast because their rods. Their what?
Their eyes aren't.
Right, their eyes
They
aren't
can only
developed.
see, so far.
Mm-hmm. I remember when my son was first born, we would take him out in the dusk, and he always really liked the dusk. It was like his eyes would get really big because he could see, sort of the stark contrast of the trees on the horizon. All right, anyway, there are different cones for different wavelengths of light.
I can tell with my son just recently, he's been really interested in the TV. It's almost like he can see the distance.
Uh-huh.
That is
Yeah, yeah. So they have different cones, red, green, and blue, RGB. And people who are colorblind, my son is colorblind, are missing one or more of these sets of cones. So my son, he's what? I think he's red-blue colorblind. That means that he can't really distinguish, say, purple from blue, for example. They just look the same to him. There are other colors that he's just sort of missing. You like colorblind? You don't have to tell me. But.
So they have those glasses that.
They have some new glasses. I don't know how they work exactly, but they are meant to allow people who are colorblind to actually see colors. But you know, people that are colorblind, they just sort of live with it, and it just becomes normal to them. So,
one time, one of my teachers, when we were talking about something similar, he told me, you know, colors are only what we've been taught. It could be really something else.
yeah, I guess so. Yeah. Okay, the retina also contains the fovea and the optic disc. The fovea is at the back of the eyeball and has a high concentration of cones. Let me draw a picture of the eye again. Here's my lens. There's this. This is the optic nerve. The fovea is sort of right here. That's the fovea. It's where the light rays focus at the back of the retina. Where most of the light rays focus at the back of the retina. And so it just has a higher concentration of light detectors there, those cones. And then the optic disc is where the nerve is attached to the eye. And so the optic disc is this part right here. There are no cones here. So you have a blind spot. You literally can't see stuff where the light rays fall onto the optic disc. But the brain sort of fills in the image. You physically can't see things where the light rays are falling onto the optic disc. And there are some images, or there are some of your rays that fall on the optic disc. But your brain, you know, it sees what's on the left and on the right of it, and so it fills in what's left. It's a small part of the image, but your brain can fill in that. Let's see, there are two types of liquid in the eye. We've already done this. We talked about this, but you could see it again. The aqueous humor is between the lens and the cornea. I remember this was where you get that condition, oh gosh, what's it called? I have it written down here. Don't remember. Oh yeah, glaucoma. When you have higher pressure. When you have high pressure inside the aqueous humor. Remember the dog with the tonometer? They did the little thing where they spit out that little pin to test the pressure of the aqueous humor. That's between the lens and the cornea. It replenishes and drains. To bring nutrients and flush out waste. And excessive pressure is called glaucoma. Remember, this was our intraocular pressure. Intraocular pressure inside the eye. And then there's the vitreous humor. It's not drained. You're born with it. Never really replenished. In fact, the eye doesn't really change shape that much. It changes some, but not that much as you get older. And really, the vitreous humor, its main job is just to keep the shape of the eye.
Does the color of your eye, does that do anything, or does it not do anything for your eye?
To how light travels?
Well, just anyway, does the color of your eye have to do with anything with your vision or anything?
I don't think so. I'm not sure. But I don't think so. All right. I already talked about the path of light in the eye, and we'll sort of see this a little bit more. But the main idea here is that our refraction mainly occurs at the air-cornea interface. So if I think about my eye again, my eye actually has the cornea, right here. And then inside of there, I also have what we call the lens. This is our lens. And both of those act to refract light, but most of the refraction occurs as light comes along here, and then it bends, and then it'll go through the lens. And then a little bit of refraction, a little bit of bending of light occurs at the lens, but most of it occurs at the air-cornea interface, when it goes from air to the cornea. Because that's where you have the biggest difference in the index of refraction. Remember, it's going to bend more if it goes from a low to a high index of refraction. And this is where I have my biggest difference, going from air over into the cornea. Going from the cornea to the lens, not really that big of a difference or a change in the index of refraction. But going from air to the cornea, that's a very large change. So that's why most of the refraction occurs at the air-cornea interface, where these indices of refraction between air and the cornea, where those are at their biggest difference. And then you can also, the aqueous humor and the vitreous humor, those are basically just close to that of water. So I said this already, but when I move from the cornea into here, that the index of refraction doesn't change that much. So when I'm changing the shape of this lens, I'm changing the focal length by very small amounts. Don't worry about this note here. It's not really relevant. So we talked about the camera. I want you to understand the difference between a camera and the eye. Right? The camera, if you want to focus on something near or far, what do you change with the camera? Thinking about the lens equation, 1 over f equals 1 over di plus 1 over do. With a camera, what do I change? Which of these variables? F, di, or do? I can change the object distance, but usually with a camera, you want to take a picture of wherever the object is. No, not with a camera.
The image distance.
The image distance. Yeah, so that's why your camera, the lens moves back and forth, because it changes the distance from the lens to where the film is, or your CCD, or whatever your camera is.
Oh, so when it focuses, it's changing it?
Uh-huh. Because when you want to focus, when you're zooming in or out, you're focusing on focusing based on where the object is. Like if I look at you, and then I try to look at Dallas behind you, my eyes have to change. I can't focus on both of you at the same time. Like right now, Dallas is kind of fuzzy, but now you look fuzzy. Okay? It's true with a camera too. So with a camera, you change the image distance for different object distances. And just to remind you, if this is my camera and my lens right here, my image distance is this distance, and my object distance is that distance. And I'll move that lens back and forth. You can change the focal length on some cameras, we talked about, but you have to physically remove this lens and then put in a new lens. But usually on most cameras you can't do that. With the eye, on the other hand, you can't do that. You can't take out your eye and then replace it with a different eye. With the eye, instead, you change the focal length. All right? So, said this before, but I want to just reiterate, because these ray diagrams are kind of complicated. I want to make sure that y'all get this. If I have an object that's really far away, I have light rays that come in parallel. So here DO is big, because when something is far away, the light rays are parallel to their axis to the axis by the time they reach me. And what that means is that they're going to focus at a certain point, and that certain point is the focal point. And the focal point is at the retina. And when the object is far away, the focal point is at the retina, and DI is at the retina. In fact, with the eye, the image distance is always at the retina. If it's not, and that's when you get near and far-sightedness. If the image distance isn't at the retina, if the image isn't being formed at the retina, that means that you just see fuzzy stuff, that you're not seeing the full clear image. When I have things that are close, I intentionally sort of draw that lens wider in the middle. So when I have things that are close, imagine I have my guy here. I think about rays originating and draw my focal points there. I draw a ray parallel to the axis and then through the focal point. And then I can draw another ray through the focal point and then parallel to the axis. And so my image is formed here. But in order to get that image formed there, I had to move my focal point from here all the way up to here. So I had to squeeze down that lens and shorten the focal point.
So did you have to bend it because of the air cornea?
No, I had to bend it. Because my object was closer. When the object gets closer, if I look at something far away and just sort of keep my eyes that way, and then I try to look at my finger, I can't see it, right? Because my lens is focused on the back of the wall. That's why my finger looks all fuzzy when I try to do this, because I'm focusing on something far away. Can you replace your eye with a camera? Oh, I think I have a video for that. We're going to skip that, though. But the answer is short, no. That camera just can't do the things that the eye does. Mainly changing the focal length, but then some other really cool things the eye does. If we have time, we might come back to that. Okay, so near and far point. So these are the nearest and furthest points at which your eye can make an image of the object. The near point is set by the most curved position of the lens. Remember, as things get closer, you squeeze down that lens and makes it more bulbous, gives it a shorter focal length. So this is the shortest focal length. And remember, short focal length means a lens that's really big in the middle like that. And the far point is set by how flat the lens can become. And that means that the focal length is equal to the image distance when DO approaches infinity. When something's really far away, the focal length is equal to the image distance. Typically, the far point is infinity. For a person with normal eyes, the near point can range. And it changes sort of as life goes on. Anywhere from 10 to 100 centimeters. So some people have a near point. That's the closest they can see, that's almost a meter away. So like they can't see their finger if they bring it any closer than this. That's why you have old people that have the newspaper. You know, like 80-year-old men that try to read the newspaper, they're holding out like this. But for most of us, our near point is right around here, 10 to 20 centimeters. Don't put your finger in front of your face. You can just look at your finger and bring it in until it turns fuzzy, and then that's your near point. You got it? That's not your near point. You can't see it that close.
You can cross your eyes.
But it's fuzzy. It turns at some point. It turns fuzzy. Like right there, I can still see it, but it's fuzzy.
I can still see.
Is that your near point? Yeah.
About
Yeah. Okay. Your near point can be pretty close as when you're in your 20s, but then as you get older and older and older, your near point gets farther away. Because remember, that lens has to be able to squeeze down. Those ciliary muscles, the ciliary body, squeezes the lens down and makes it wider in the middle, so you can focus on things up close. And that means as you get older, the lens gets more rigid, the muscles get weaker. It's just, 40 years of using your eyes is just, hard on them. So a few vision problems: nearsightedness or myopia. So the near and the far, that refers to what you can see. So like I can see things that are near. So nearsightedness means that you can see close things but not far things. Nearsightedness or myopia. The image forms in front of the retina. So nearsighted people have an eyeball. I'm exaggerating. But they have an eyeball that looks like that. That is not spherical. And so when I have light rays that focus, they focus short of the retina. That's nearsightedness. It means that the eyeball is too long, and it doesn't mean that there's a disease or anything. It just means that when you were born, that your eyeball was a little bit too long than it needed to be.
So then what if the glasses do form? Does it change the...
Yeah, the glasses will give you two lenses, and it'll change the focal point. So when you put a lens in front of here, it'll shift the focal point back to here. It's very simple, actually. I mean, we've had glasses for hundreds of years, thousands of years, I guess. But when I put a lens here, let's see, what do we do? I don't know, we do a concave lens. It shifts the focal point. It actually shifts the light out and then allows it to focus back there. So it thins the light out and goes, and then it comes back at the retina. So nearsighted people can't see far away things. Their far point. What is the far point usually for people? No, that's the near point. The far point is usually infinity. That you can use. It's really not much work for your eye to see things that are far away, right? To see things up close, it's a lot of work. That's why you get eye strain when you read a lot. But to see things far away is pretty easy for your eye because your lens just sort of relaxes into that shape. But the far point for these nearsighted people can be really short. It can be about 20 to 30 centimeters. So that means they can see something this far away, but anything beyond that is just fuzzy. My wife is nearsighted. So if she came in here without her glasses, she could sort of see colors, and she could see blobs where you are, but nothing more. Are you're nearsighted too?
Yeah.
Yeah.
And that clock right there, what's it called for glasses? It's called.
Well, the optometrist tells her that the good news is that as you get older, and she just turned 40, so she's beginning to develop presbyopia, which is a farsightedness condition, that as you get older, that your eyes will gradually get better before they get worse again.
So what is it where it says the eyeball is too...
Oh, the eyeball is too long. Oh, this is a picture. So this is a picture of, I'm sorry, I drew this, but this is myopia. So the focal point is here. I put in a concave lens, and that causes the light rays to bend out, and then they bend back in at the right point. Use a diverging or concave lens to correct this. Don't worry about this sentence. Hold on, give me just a second. We didn't talk about virtual images, did we? We did talk about virtual images?
Oh yeah, where they can't be protected.
Yeah. Right,
Yeah.
right.
But you know, like what in test, previous test or whatever I was saying, it's something about would be.
And I knew it was.
Yeah. Let's talk about it here. I'm not gonna take this out, actually. I'm gonna take this. Sorry, I know y'all can't erase as easily as I can. I'm sorry.
Yeah, it's, one over on page 91.
Yeah, yeah. So, a couple of things about the lens equation. Just the numbers that occur. You can have a positive, or a negative focal length. A positive focal length is a convex lens, and a negative focal length is a concave lens. Right? If you've been to the eye doctor, you might have noticed that some of the lenses have a negative power, and some of the lenses have a positive power. Negative power lens or concave lens. You have negative power lens. Reading glasses, which are convex lenses, they have a positive power. They're +1 1/4, +1 1/2, +2. That's their power. That's 1 over the focal length. Remember, P, the power, is equal to 1 over the focal length. In a similar way, DI can be positive or negative. Plus DI is a real image, and minus DI is a virtual image. Plus DI is a real, minus DI is a virtual. So if I use a diverging lens, that is, if I have a negative focal length, it shouldn't be too big of a reach to imagine that my image distance is going to be negative. Then I'm going to have a virtual image. Remember, with our virtual image, these can't be projected onto a screen. So if I think about a convex lens, let's say that I have light coming in from this direction. It doesn't really matter what the object is. But if I have an image over here, this is a real image. Actually, it turns out that that real image is inverted, but it doesn't matter. You know, let's go ahead and write it that way. But this real image is inverted. I have some object that's over here. It's my object. My real image is on the opposite side of that. So if I were to take a screen and put it right here, then I would be able to see that image on the screen. And it would be upside down. This, by the way, is how your eye works. So everything that you see is actually upside down, because you have a lens that creates a real image that's upside down. Fortunately, your brain is pretty smart. That your brain takes all the image, all of y'all are upside down on the back of my retina, and I'm upside down on the back of your retina, but your brain says, no, that can't be right. That just doesn't look right. And so it flips it up right side up. Have you ever seen those glasses that you can buy? You wear them, they have like a prism in them, and they turn everything upside down. And then you walk around for a little while, and eventually your brain says, no, that can't be right. And it turns the image right back up again. Your brain's kind of cool. It does a lot of interesting stuff without you even really thinking about it.
I think that it's like a motion picture. It's like your brain fixes all the things that your eye can't.
Uh-huh.
And just like a motion picture, it becomes
Yes. Yeah, your brain, it's similar like when you're riding in a car. And you're riding in a car, you're not driving, you're looking out the window at the passenger side. Those things are zooming by, right? But your eye and your brain that does it involuntarily is able to sort of take snapshots along the way and make those into still images that you can actually see. Because otherwise, if you were just looking, you wouldn't really be able to see because it's just going by so quickly. So kind of a cool thing. Okay, real images. Real images have a positive image distance. Virtual images, on the other hand, this is a virtual image. A virtual image is on the opposite side of the lens. You can't project this onto a screen. It's sort of hard to think about how we get an image on the opposite side of the lens, but it can happen. The magnifying glass that we did earlier, remember I passed around that big lens, and you created an image of the lights onto the paper? That was this. The magnifying glass, on the other hand, produced an image that was on the same side of the lens as the object. Okay? So real and virtual images. These have a negative DI. Negative DI. So you can use a diverging lens to correct for nearsightedness. The virtual image created by a concave lens or diverging lens, remember those are same, concave and diverging, appears closer. So what it's doing is, let's imagine that your real object is over here. This person that is nearsighted, that they can only see things that are close to you. This is my object. This diverging lens right here actually creates an image that's closer. And so the nearsighted person can see close-up things, so it can now see this image of the object that it couldn't see before. This thing makes the image up closer. And notice this is a virtual image, right? Because it's on the same side as the object. If I were to put a screen here, I couldn't see the image on the screen. I would just block the light from the object. So that's what these concave lenses do. They make the object appear closer to that person. Or they make the eye think that the object is closer. Okay, so you can use the lens equation to find the strength of the lens for a particular person. We're going to skip this part. I really am going to erase it. All right? Just know what strength is, that if I know the focal length, then well, we can find the power, the strength of the lens.
So glasses can also be the plano and bi?
Yeah, they can, but we'll just sort of think of glasses as either being biconcave or biconvex. You do need to be able to identify those plano convex and plano concave, but just in a picture. I might give you a picture. Okay. You can identify a nearsighted person by examining their glasses. We talked about this. They are concave or diverging, that are wider on the edge. And also the person's eyes should appear smaller through a diverging lens. I think that glasses today, they're not as obvious. Do your eyes appear smaller? It's harder to tell. But you've seen movies where they put the glasses on, their eyes are really big. Those are farsighted, or near farsighted people that have convex lenses. All right, so
The bifocals, they used to be huge, but now they're just.
yeah, they're a lot better at making lenses.
Yeah, she said they used to be really expensive. I mean, they're still expensive, but not as bad as they used
Yeah.
to be.
All right, farsightedness, or hyperopia. Images form behind the retina. So focal points there. So that means that before your eye was too long, now your eye's too short. There's nothing wrong with you. It's not like you have a disease or anything. It's just that's how your eye forms. So usually the eyeball is too short. Farsighted people can't see near objects. Yeah. Their near point is farther away than normal. All right, you can see up here, a farsighted person might only be able to see up to here, and not closer than that. Use a convex lens to correct this. The image of the object appears farther away. And this is like a magnifying glass. That's what reading glasses are, effectively, magnifying glasses. All right, so just like, remember with nearsightedness, the lens made the object appear closer. These make it appear farther away. Because the farsighted person can see far away things. They just can't see close things. That one's a little easier, but you need to know hyperopia, myopia, what the effect of those are. Can you see far or near? What causes them? A short eyeball or a long eyeball? And then what kind of lenses do you use to correct them? Convex or concave? You got that? The name of the condition, what causes it, long or short eyeball, the effect of it, you can see far or near, and what you use to correct it, convex or concave.
So when they do LASIK, what are they fixing?
They actually go in and fix the cornea, I think. I'm guessing. I'm not a doctor, so I think it's the cornea. Has anybody ever had LASIK? No?
Doctors did.
Yes, somebody that I can call. All right. Now we can finish this. So age-related problems, there are only a couple, presbyopia and astigmatism. We talked about the presbyopia. Yeah. Presby is like Presbyterian, which means elder. Presbyopia is farsightedness. But it's different. It's not because of the shape of your eyeball. The near point increases with age. So as I said, presby, that's equal to elder. And the person can't see objects that are nearby. They're farsighted. But not because of their eyeball. The lens loses its flexibility, its elasticity. And you use reading glasses to correct. You don't even need to go to the doctor, you just get reading glasses. And remember, these are concave or convex lenses? Convex. The convex lenses for farsighted people. Farsighted people and old people use reading glasses. And then astigmatism. Usually, with a lens, you only have one focal point. But with an astigmatism, the lens might have a focal point there, but then you might also have a focal point here, a focal point here, you'll have all sorts of different focal points. And it'll depend on the angle that the light is coming into the lens. You just get all mixed up. All of your light rays get mixed up inside of your eye. So with an astigmatism, the lens is not spherical, but it's oval. And the focal points are different depending on the axis. And this can be corrected with lenses that also have different focal points. So the optometrist will come in and figure out, okay, if light is coming in this way, the focal point is this. If it's coming in this way, the focal point is this. And they'll create a lens that also has different focal points depending upon the axis that the light is coming into your eye. And it'll correct for those different focal lengths.
That sounds really interesting.
Yeah, it's pretty crazy.
Is that where their eye kind of like moves a little bit when they're trying to,
I don't know. I'm just going to give you the answers here for these. This is a converging. A nearsighted person cannot see distant objects. The sensory layer of the eye is the retina. Don't worry about this. Light entering the eye refracts the most at the cornea, and the lens of your eye forms a real inverted image, so 1 and 4. Alrighty? And there are 2 sections in your book. Other methods of vision correction and other problems not on the test. I don't know what pages those are, but those are the headings. Other methods and other problems not on your test. Alrighty? Listen, I'll be around a lot in the next week or so. So if y'all, as you're studying and preparing, if you need help, if you want to sit down and sort of knock around ideas or get help with particular topics, I'm available. You got a question, Kate?
Oh, X out. That's not going to be an test anymore.
Yeah, I'm not going to do any grade tracing, at least not for that level. What we did, like in this was basic grade tracing, but not that. Okay? Yeah.
Any particular format for the bigger eye could be on a paper?
No, you can use APA or whatever it is that you use. I know different papers are different. As long as I understand it. Okay? Papers will be due on Thursday at midnight. I'll post it on Moodle. I have several of you have sent me yours. I'll get back to you today, hopefully. I will get back to you today. Or maybe early morning tomorrow morning. Okay? Have a great day. See you on the 12th, if not before.
So it's just going to be stuff.